two kinds of technical words in physics to describe infinities. There's one that's infinities that are normal infinities, and that's usually an infinitely small quantity. Two infinities, right? One is an infinitely small quantity, so it can easily be discarded, right? It doesn't really matter. 0.0000 somewhere down there, it doesn't matter. Okay? That's one kind of... Then there's another very highly technical term you find in physics documentation called nasty infinities. Nasty infinities are infinitely large infinities that creeps up in your mathematics, in your equations, in your conceptual physics. And those are thought to be nasty because when they creep up, it's not like you can just make like it's not there. It's an infinitely large quantity. You can't just sweep it under the carpet and like avoid the whole thing. Well, they did a real good job at avoiding this one. But in general, it was not accepted as a valid theory if your theory breaks down into infinities at its results. And so instead of discarding the concept, they did something that they called renormalization. They used the infinite potential of the vacuum and basically took the Planck's distance and took the 10 to the, what is 1.616 multiplied by 10 to the minus 33 centimeters. So that's a very, very, very small dot. Notice, though, that the 1.616 is very close to the 1.618 of the phi ratio. And they took that distance, like that very teeny point, which is now billions of times smaller than the nuclei of an atom. And they said, well, that is fundamental to creation. And if we put the number of these little dots in a centimeter cube of space, of vacuum, we will have a finite density for the vacuum fluctuations, for the vacuum density, the energy in a vacuum, in a centimeter cube of vacuum. So here it is. They took a centimeter cube of vacuum. They took a Planck's distance, teeny point, and they stacked them into that cube. And then calculated how much density of these quantities would there be in there to get a finite number. The result is 10 to the 94 grams per centimeter cube. 10 to the 94 grams of centimeter cube. That's 10 to, with 93 zeros, you know, following it. It's an extremely large number. When I'm dealing with a number that large, and it came from a renormalization, my tendency is to think that we're talking about infinities. Okay? Because if you want to get an idea of what density that means, imagine you have a centimeter cube of space that has all of the stars in the universe condensed into it. Like all of the stars we see with the Hubble. Okay, all the galaxies, everything we see, we just put it all in a big trash compactor and we just squash it all up into a centimeter cube of space. All right? Imagine how bright that would be in one way, but never mind that, then you still wouldn't have the vacuum density. You still would be short from the density of energy that is calculated to be in the vacuum at the quantum level. That is a lot of energy, folks. And so, how did this infinite amount of energy divide and create subatomic particle, an atom, to me, that was the question. To me, maybe the vacuum energy had structure. Maybe the vacuum energy wasn't just a random fluctuation like this, but had a boundary fractal structure, had a geometric structure to it. I didn't know why at the time. I didn't know how I could prove that. I didn't know how I could describe that. But I wanted to explore that thought. I started to see that maybe, just maybe, everything we see in the universe is just division of that energy density of the vacuum in various scales. To me, there was some logic to it. Well, that brought me to eventually a meeting with Elizabeth Rauscher and a collaboration with her. Elizabeth is a very respected physicist that has received medals of honor for her work in black hole physics in the 70s, has worked with John Wheeler, many other very famous physicists. And Elizabeth and I got together, and Elizabeth had written very advanced computation and mathematics for a unified field theory in the 60s and then in the 70s, and she could never kind of get the whole key put together. And you know, when we met and I talked with her for almost 3 days, I was able to fill in a lot of things, but she didn't know, and we had to talk some more, and we had to run some calculations and all this, and she was definitely skeptical, but we started to write things, and then we thought, well, okay, if this is true, then if we look at a large scale in the universe, we should start to see very specific divisions. We should start to see structure. If the vacuum is dividing under very specific structure, then we should be able to see it. We should be able to calculate it from what we observe. So we decided to write a scaling law. And this is what came out. This is a paper that's unpublished at this time. I'm publishing other papers in the scientific journals right now that are the foundation of the change I've made to Einstein's field equation. This will follow. We presented this at the American Physical Society in Albuquerque, and here and I've presented it as well to some of the directors of the telescope here on the Big Island, and many other astrophysicists and physicists. And usually I get a pretty good reaction out of it. It's kind of, you know, jaw-dropping. What we did is we took the radius of objects, okay? And so here on the in the x-axis is the radius. And here is the frequency of these objects, the fundamental frequency of these objects in hertz. And the energy level of the object is pretty well described by its frequency. So you could think of its energy level as well. If you take the size of the universe, that is, if you look at the way the universe is expanding, you can extrapolate the size, and if you look at all the matter that's in the universe, when you place that amount of density, when you place all that matter in Einstein's field equation, the result is that the universe is too dense for light to escape it. That is, we live inside a black hole. And, you know, that was expected from me. I thought that earlier, and then I realized that as well from my own calculation before, and I thought that would make sense. Because remember, I was thinking that if for every expansion there's an equal and opposite contraction, then everything can be divided to infinity, then everything would have infinite density at its center. Everything would have what we call singularity at its center. And so I thought everything is just a different size black hole. And so I wasn't surprised about this. So we placed the data point for the universal, the 10 to the minus 17 is the universal frequency based on our calculation, and the radius is 10 to the 28. And then we place the next data point for the for quasars. We're taking average size and frequencies of quasars. This is a very large scale, so it's acceptable. And we place the data point. And it surprised us. It was a fairly good linear progression from universal size. Then we place the data point for galactic centers. So we're getting smaller in scale. And again, an average galactic center oscillation rate and radius. And we place the data point, and again, linear progression. Then we place a data point for solar dynamics, stellar dynamics, and we got a linear progression again. That was astonishing. I mean, there is nothing in standard views that would predict that, other than the view I was getting that the vacuum is dividing itself under very specific structure boundaries. Then we went all the way to the atomic level with the radius and fundamental approximation of frequency for X-ray emission. And we got a data point that was a perfect linear progression again, but this time across the boundary of quantum theory into the atomic level. So now we went from cosmological object to quantum theory level. And this is one of the fundamental fractures in our current physics. Quantum theory and relativistic physics don't agree. They don't work for each other. So that was really exciting. And then we went all the way down to the Planck's length and placed the Planck's length dot data point and at 10 to the minus 33, and sure enough, the progression was perfect. And that got us very excited. I mean, definitely it supported what I was trying to explain to Elizabeth and our discussion, and we started to really get some steam going, and it was really exciting to see that happen. And we thought of publishing it, but I wanted to publish first very fundamental physics to be able to explain this, not just the phenomenon. The other thing we noticed is that if you take the distance between the data point, which is kind of nice, it's sweet, and you divide them, you always get very close approximation to the phi ratio. The phi ratio is 1.618 and is, and goes to infinity. It's typical to find it in nature everywhere. You find it in flowers and shells and pine cones. You find it in the way tree divides. You find it in your body. There's a phi ratio between the end of your finger and the second part of your finger, and there's a phi ratio between the second part and the third part and your hand, relative to your fingers, and then your fingers and hand relative to your forearm, and your whole body is built like that, and so on. And so you find it in nature everywhere. So to find it on a scale that's so large was very exciting, because it supported that this would be something that nature would naturally do, that space, that the vacuum would naturally divide itself under these very specific fundamental mathematics, because we observe it in nature everywhere.